Welcome to Broadcasting Common Ground, the Deep Foundation Institute's podcast channel. In this series, DFI's Rumble, we will be speaking with opposing industry representatives, asking hard questions and facilitating a polite argument. In this episode, Paul Axtell and Greg Canivan explore the history and current practice of dynamic pile testing. Sponsored by ECA.
Welcome to DFI's podcast, Broadcasting Common Ground. I'm Lucky Nagarajan, and welcome to Rumble, where we ask two guests to enter the arena and go toe-to-toe on topics relevant to our industry. The referee facilitates the discussion. In this episode, Sebastian Lobo-Guerrero referees the discussion between Paul Axtell, COO, Senior Principal Engineer, Dan Brown and Associates out of Kansas, Greg Canivan, Technical Principal, Senior Project Manager, S&ME out of South Carolina. Sebastian, can you give us a hint of what is in store for us today?
Yes, Lucky. Thank you very much. Yeah, we had a great discussion about pile dynamic testing, and I guess the good, the bad, and the ugly about it. So we're going to investigate different things and different applications, and why is the best thing in the world, and why it could be the worst thing in the world. So that's to come.
Is it imaginary versus reality?
We will find out.
Thank you, Sebastian, for that. And thanks to Paul and Greg for joining us. Looking forward to how the first round is going to go.
Excellent. So I guess let's get started, right? So yeah, so as we mentioned before, we have Paul and Greg today to... Oh, come on, we started like that. We were gonna have a little intro before here, but anyway, we have Paul and Greg, two very well-known figures and references in the Deep Foundation industry. So some, two good friends of DFI. I don't know, Paul and Greg, if you guys want to mention a little bit about yourself, and especially related to like PDA and what we're gonna talk today. So I guess let's go in order. Let's go civilized. So Paul, if you want to start first.
Sure, thank you. Yeah, so Paul Axtell, Dan Brown Associates, maybe 22 years out of experience out of graduate school, the last 15 of which have been with DBA. My distinguished opponent, Greg, a colleague of mine, someone I have a lot of respect for, and more importantly, a guy that I call a friend. So I'm really grateful for the opportunity to be here today and look forward to a fun discussion.
Excellent.
Well, thank you for that. When I heard I was rumbling against Paul, I busted out the boxing gloves, and then I realized I got a button-down shirt on, and who brings boxing gloves to a rumble? So I know Paul's from the big city of Kansas City there, so I got my work cut out for me. But my name's Greg Canivan. I live in Charleston, South Carolina with my wife and two kids, and been practicing geotechnical engineering for about the last 25 years or so. Got my degree from Clemson University. Go Tigers. And yeah, a lot of, I guess my career putting food on the table is revolved around dynamic testing. So I don't drink the Kool-Aid per se, but I do believe in it, and it's a great tool for our industry.
All right, no, excellent. Thank you very much both for that introduction. So I guess before we engage into battle, let's just kind of talk a little bit what PDA is and the revolution that it's been. So I guess, Greg, if you want to just mention a little bit, if you want to summarize just like the history, right? I mean, I'll just give you my angle. When I started my career, and keep in mind that I started in Colombia, PDA was not available, and then it was the engineer's equation, right? It was basically correlations that based on refusal, you could try to correlate and see what is the capacity that pile is having, and maybe what is the stress. Equations used to be really, the engineer's equation was very related to the pile, that hammer that you were using and things like that. And then obviously PDA came into the market, and we start, having the wave equation analysis and all that. So if you want to just mention a little bit of that, and how that, let's say, how PDA came into your life, right? And what it means.
Right. Well, I guess there's the wave equation type stuff that was around in, I guess, the middle of the 1900s, and the PDA was kind of pioneered in Ohio by Dr. Goebel, with Frank Rausch doing a lot of the CapWAP, which is the subsequent analysis after the field work, and Garland Likens, who established GRL and kind of made a commercial version of the machine that I use anyway. Yeah, and I think a lot of people focus on the capacity or bearing resistance, let's say, use with the dynamic test method, but there's also a lot of other interesting things that you can get from it as well, including driving stresses, hammer performance, and those kind of things. I kind of liken it a little bit to in situ testing, say with CPT versus SPT, where maybe the SPT, you get a blow count every 5 feet, whereas the CPT, you can get a continuous profile. And sure, you can't put your hands on it, but as engineers, we don't necessarily need to put our hands on it. We're looking for how things perform. So the feedback from the PDA as you're installing a foundation is you get basically a feedback every blow.
Correct. And yeah, Paul, I don't know if you want to also mention a little bit. And before I pass to you, I have to mention, Greg, on something that you said. I did took a class on PDA and drivability of piles in Cleveland with Dr. Frank Rausch in, I don't know, like early 2000, mid 2000s. And it was beautiful. I mean, just understanding everything from him. And I think before we start into anything, we have to recognize the amazing job they did, because they changed our industry, right? I mean, that these completely changed everything. But Paul, if you want to basically say something similar in terms of how do you got into PDA and what it means to you.
Sure. I'll just start with full disclosure. I'm not a PDA, or I think we should be using the term high strain dynamic testing. I'm not a high strain dynamic testing technician. I've never been the one to climb the leads and attach the gauges to the pile. I look at the results of high strain dynamic testing probably on a daily basis, if not weekly. When I first got interested in it, I guess would say it was in graduate school working on soil dynamic research with Ken Stokey. That certainly was not high strain dynamic testing like we're talking about today, but the principles of soil damping, wave mechanics, all the things that are germane to dynamic pile testing, the basics of the principles of it. That's where I first learned it. Early out of graduate school, I was fortunate enough to work on a very large project in which high strain dynamic testing with restrikes and signal matching was conducted at several sites, along with static load testing. And the results, they didn't compare very well, to be quite honest with you. And I think that had a lot to do with the system that was being implemented, as well as the soil conditions. And so I will echo Greg. There's a lot of benefit to high strain dynamic testing with respect to monitoring the hammer energy. The in situ evaluation of stress in general terms is also very useful. I will say, oftentimes we hang our hat. The stress that we're measuring may not be the highest stress or local stress that could be occurring, but it's still a useful measurement. Where I will start some conflict is, I do believe that the ability for high strain dynamic testing to accurately estimate the static resistance of a pile is oversold. It isn't always the case. There are some geologies and driving systems where it works great. There are lots of other locations that I don't think it works so well. And I feel like our industry doesn't broadcast those situations enough. And sometimes we may listen to saleswomen that may give us the impression that it is the right answer all the time. And I just think that that's oversold.
All right, man. I can feel already we're gonna have a really meaningful discussion.
I feel my blood boiling already, Paul.
Yes, I was trying to be civilized, but he's bringing us down. But no, that's the whole point today, I think, is to talk about this example. And I think that's what is gonna bring a lot of value in our industry. So, all right, so let's get started with the good, the bad, and the ugly. So let's start with you, Greg. Why don't you provide us an example where PDA and CAPWAP have made a positive technical difference? I mean, something that you can say, okay, this is the reason that, that this is so awesome.
Well, I go back, like I said, I think that high strain dynamic testing is not just about capacity, but it's also about hammer performance and things like that. And I go back to a project I worked on years ago, an interstate project, where after 4,000 blows on a large diameter pipe pile, the driving was at refusal. It was about 20 blows an inch, 10-foot stroke. The hammer was maybe a D36, so 70, 80,000 foot-pound hammer. And it was transferring about 30 foot kips. So say it's 40% energy transfer, something like that. So it was stroking pretty well, we got some stress measurements, were below the limits. and it mobilized, say, 250 tons is what we were measuring, which was below what they needed. So we stopped for about an hour and decided to restrike the pile. And when we did, after about an hour, the blow count dropped to about 11 blows an inch from 20. The stroke height dropped from 10 to 9. And everybody was concerned about relaxation and things like that if we had a loss of capacity. But actually, the PDA showed that we got a little bit more energy into the pile, about 50% versus 40. And we were actually able to mobilize about 300 tons. So there was no relaxation, and we actually measured more resistance on the restrike. But it really, to me, drove home the point about how driving systems and things can change their efficiency if they get overheated, times of the day, these kind of things. And I'm a board member of the PDCA, and their tagline is "A driven pile is a tested pile." And somebody once told me, sometimes that can come back to bite you if people hang their hat on a blow count with such ferocity that you must get this. But that was really a time where the stroke got lower, the blow count got lower. People thought it was relaxing, but actually the hammer performed more efficiently, and we mobilized more resistance. So I think that was a really good case across the board of some of the things high strain dynamic testing can help us with. I guess as far as the bad, my personal, here in my area, we drive a lot of concrete piles, and sometimes if you get these hairline tension cracks, that can really make the dynamic testing difficult with respect to capacity. The field values can be all over the place, and the cap WAP gets pretty rigorous, the signal matching that you have to do. So the bad is sometimes with cracked concrete piles, not cracked so much that you can't drive them, more the hairline tension cracks. And then of course, nowadays with the open-ended pipe piles and the plugging effects, the soil plugging effects, and trying to measure that with dynamic testing is difficult. I guess the ugly is maybe, I mean, I don't know that I'm much to look at now, but you should see me sometimes after I've had a hard day out in the field. But it's ugly from the standpoint of you can get yourself into some really crazy situations, but that's also, I think, something that's really neat about the high strain dynamic testing is where you can take this tool. I mean, you can do it below water, down in coffer cells. If you can get a hammer on top of the pile, you can do this test. So you can really get yourself in some nasty, dirty, ugly looking places, but still get some really, really good information.
No, I agree, and I'm gonna be taking sides and changing that, as we go. But yeah, if we're talking about the good, I also have great experiences through my career with the good. One important thing that you said is not only capacity, but it's also stresses, right? And when I started, we typically only use PDA for friction piles, and piles that were going into rock. It was always the thought of, why do you need that? You're gonna eventually go into rock and you get refusal, that's it. And then it was the reason of saying, yeah, but it's probably still useful to have PDA because then we know that we didn't overstress the pile and we get a capacity. And then, there is plenty of examples that I have that we have used PDA, let's say for pile relaxation, right? And evaluate things of pile relaxation that it definitely brings us, like, let's say that we get extra safety because even though we have pile relaxation, we were still in a good range from where the pile needed to be, so we could afford that. Same thing if we talk about pile setup, right? I mean, I'm sure everyone in their careers have had pile setup, driving piles, on friction piles on saturated loose deposits of sand that when you start driving and you see that you have half of your resistance, you get panic, right? And then after you wait a little bit and the pile setup, of course, you confirm that the capacity with the PDA is there. So definitely there is positives, and I think we all recognize that, right? But I guess to try to spice it up, let's go, Paul, with you, and let's kind of do things a little different. So why now you tell us one experience, and obviously feel free to interrupt each other if you feel that the other one is saying something that you don't agree. But Paul, if you want to, or kind of go
Sure.
against something that he said, but if you don't have comments, or if you want to say that and then the question, I guess my question would be, why don't you give us a good example where PDA or CapWAP was the opposite? That was a really bad disappointment, and you kind of felt that the technology left you down.
I will. Thank you. First, though, I'm going to go with real briefly with my good, bad, and ugly. I will say my good is just like Greg said, the ability to monitor the hammer energy is it's a tool that it's undersold. It's undervalued, I believe, or at least it's under proclaimed in the world of selling dynamic testing. Like Greg, in a project in Western Montana, I've had that same. If it weren't for high strain dynamic testing, I would have been stopping piles shorter than they should have been. It was just like you said, an instance of the hammer heating up and losing energy, and would have never known that by standing on the ground, counting blows, watching the stroke, watching the jump stick. Without high strain dynamic testing, I would have never known that the right amount of energy was not being delivered as the hammer heated up. So that certainly is a good part of high strain dynamic testing. The bad, there are soil deposits, there are driving systems where the estimated resistance from high strain dynamic testing is not it's not the right number. That's the bad part in my mind. Now, maybe the majority of locations, maybe that's not the case, but there are locations that are out there. There are geologies, there are hammers, there are piles, there are soils where it doesn't give a good estimate. So that's the bad. And the ugly, I think, is another part that I think goes under notice in our industry, and that is it is not a unique solution. There is scatter. It is operator dependent. It is interpretation dependent. And I think worldwide, there's lots of scatter on who the right operator is, who the right technician is. Sooner or later, someone's got to pick some squiggly lines and draw a conclusion, and there is scatter. And I think that's the ugly part of the industry. And when you have maybe a less sophisticated owner or client, they're looking for a number out of the box, and they may not appreciate all the subtleties that go along with it. So I think, in my mind, that's the ugly. So I guess I'll stop there and let Greg shoot back.
Yeah, Greg.
Sure, I'll jump in there. Like I said, I use the tool. The number that you get out of at the very end needs to be evaluated just like any other number. So I would say, first of all, and there's been some studies and some neat papers written about asking folks to take a boring log or CPT sounding and say, we are going to drive an H pile on this site. Use whatever method you want. It may be a method that somebody uses on from a database on a concrete pile in sands in Florida, and this site may be in the Netherlands, but they're going to use their formula that they're comfortable with no local knowledge, and they're going to come up with their estimate of what the quote unquote resistance is. So once you look at that kind of data and see what's the scatter in the prediction, it's off the charts. Then if you come back and say, do a dynamic test, and you give everybody that data and you do signal matching, yes, not everybody will get the same answer. And there will be some scatter. There's been a lot of studies, and the scatter might be plus or minus 10%, maybe 20%, something that high, but probably on average, maybe plus or minus 10%. But the kicker to me is, what are we comparing it to? And if we're comparing it to a static load test, which I'm sure y'all both have run static load tests, for some reason that's thought to be the answer.
It is the answer.
Why is not? Why is not the answer? Because I agree with Paul. The static test is the answer. I put the pile, I put the load, and I measure, right? That's it. Why not?
That's the answer.
So when Paul says the bad is the answer from the dynamic testing is wrong, I think what the dynamic testing really shows is the good, bad, or ugly of the soils that we're in. With a static load tests, you get 1 point at one depth at 1 point in time, essentially. And that's what you're comparing, say, the dynamic testing to. You have to compare apples to apples. And if somebody runs a dynamic test in a shale and says, this is your resistance, it's not necessarily that the dynamic testing is wrong. It's just that the soil may relax and they're providing you a number in a geology that at that time, that may be the resistance, but that's not the long-term resistance. So I'm not sure if that's where you're going, Paul, but I feel like that's not necessarily the dynamic testing issue. It's just the fact that the resistance changes with time, and at the time it's being reported, it's maybe correct, but that's not necessarily the long-term resistance.
Before, Paul, before you answer, I will just say, let's try to establish, just to clarify. So I guess, Greg, do you agree a static test, I know limited to the place that is done, and it's 1 point, one specific location, just within the inch or whatever that we're talking. If you do a test there and you do a static load, that is the answer.
No.
You don't agree on that? But
No,
why not? If I load it and I see capacity.
Paul, our esteemed colleague, Tim Siegel, has a beautiful paper that I steal a figure from all the time. It's a static load test on a CFA pile. And the test is taking to failure using the Davison criteria.
Mm-hmm.
It's also plots out the failure criteria that the IBC references, say De Beers, or there's a couple that the IBC references.
Okay.
So from one plot, you have 3 different ultimate resistances from that test.
Okay.
And not only do you have 3 different ultimate resistances, the values are something like 500 kips for one and 250 kips for the other. So the same exact test results in an ultimate resistance that's 2 times the other result. But I go back to,
it's only half the
cares
battle.
what the
Though,
ultimate
Greg.
necessarily is. If you go back and you look at, say, 200 kips on that curve, the pile top may have only moved 1/3 of an inch, 1/4 of an inch. So the ultimate resistance doesn't necessarily affect the performance of that foundation closer at the actual design load.
So Paul, before you unleash all the ammunition that you have, just to be absolutely clear. So I guess, Greg, what you are saying is, my point was, one test, one static in a location is representative. And what you're saying is the interpretation of that, it's subjective because there is different methods, right? And obviously, depending what you are calling, it's not a perfect curve that goes this and that, right? And depending where you call it, even your ultimate is subjective to change. And you are kind of elaborating also on the defense of the squiggly line that you say, well, in PDA, you may criticize that, but it's not that different on your interpretation of static. Just to summarize. So now, Paul, you can take it from there and relieve the pressure.
So, Greg, I hear what you're saying, but I think that's a fundamental flaw in the interpretation that is specified to us by our codes. The load settlement behavior of the static load test is the answer. Whether we apply it incorrectly due to code requirements or maybe even our own ignorance, whether we apply it incorrectly in design is a separate issue than having the real data. Under a static load, there's a deformation of the pile. That load settlement curve is the answer. If we choose to screw it up by our interpretation and application, that's a different animal. But the answer is unique. The application is not unique. I think that's the difference with high strain dynamic testing. High strain dynamic testing, I mean, and I think if you dig into the literature, it's published right there. The effect of dynamics on soil shear strength, it's profound. And to be honest, not very well understood. And so any way we slice it, high strain dynamic testing, it's in the title, it's dynamic. And so there are effects, pretty major effects on the shear strength of soil that in some deposits don't lend themselves very well to high strain dynamic testing and measurement. It's not imaginary. We're measuring something. It's just we don't know what we're measuring.
Greg, you want to counteract that?
Sure. I think that's the magic, so to speak, of the high strain dynamic testing, right? We know that the bridge or the building can only rely on the static resistance. What you're measuring with the high strain dynamic testing is both the dynamic and the static resistance. And so you have to separate out the two. That's like I said, that's the magic of it.
That's the voodoo of it.
Well, and what I go back to sometimes is even, you have the signal matching, which, sort of refine some of your field values. But, it's like anything, garbage in, garbage out. You can also use some of the more, basic case method type things. And from that response of the pile during the test, your CAPWAP shouldn't vary too much from those methods. But I think over the years, these questions that you're bringing up, Paul, have been studied and vetted and analyzed. And I think it, like anything with geotechnical engineering, local knowledge is the key. And if you know that time and time again, you have some sort of soils that just don't fit this model where the dynamic testing is having a hard time. But I still would wonder how the static load and the dynamic load results vary, how much they vary, and why these soils that you're talking about are so unique that the dynamic testing just can't measure it correctly.
Sure. So the magnitude of difference is about 30%. So in all cases, I've seen the high strain dynamic test with signal matching on restrike in the same time frame of the static load test. So let's take the time, the setup out of the picture. We're looking at about a 30% underestimate, and that's not just at one site. That's at about a half dozen sites, most of them in the Midwest, but from Minnesota all the way down to Texas, really. Most of them in recent alluvial deposits, probably with a high degree of sensitivity of the soil. So, if you think of sensitive soils and the effect of the dynamic loading on shear strength, I think we could all wrap our minds around that those would be prone to deterioration at a rate that we don't totally understand, to the point where if we're doing a restrike, if we don't capture it on the first 1, 2, 3 blows, we've changed the conditions. And so restrikes, they can be useful. Heck, I use them all the time to get myself out of a bind. But the reality of it is that's not necessarily the right answer either. But I wrote down a note, Greg, when you said local knowledge is key, and I totally agree with that. And I will also admit that there are geologies and experiences where high strain dynamic testing is a perfectly valid method to estimate static resistance. But I got to ask you the question: when you say local key is knowledge and we know we're getting the right answer, what is that calibrated to? And I think the answer is a static load test.
Yeah, I mean, I'll give you some of these. Like I said, I'll hear you out. I'll swing and duck and hear you out. We want the right answer, but for some reason, I still go back to the fact of when I do a project and I provide somebody a shallow foundation option, I tell them, if you design your foundation for this bearing pressure, you will have less than 1 inch of settlement. For some reason, when we get into deep foundations, and this is not necessarily only dynamic testing, we're so focused on capacity. And I hear you. We want to try to get the same. We want the right answer, really. Whether it's the same wrong answer, that doesn't do us any good. We want the right answer. But I think that sometimes, even if the answer is variable, we still have to go back to the performance of that foundation. And if we're, again, I don't know the details of where we're off by 30% potentially, and that the CAPWAP, the signal matching output, you do have a load displacement curve that's presented there, but basically everybody just looks at the dynamic test results as the ultimate resistance, which again could be similar to what I was talking about earlier, where that's the interpretation of the dynamic testing, is that ultimate, very, very, very end of the road resistance. So if you're comparing the static load test to, say, the load test curve on the CAPWAP, are the performance, the load versus displacement, accurate with each other within the area that the load is actually on? And maybe we're arguing more about what's happening at the tail end of the result.
So totally agree that maybe the industry is too focused on capacity. But again, I mean, as you alluded to there, it's the load deformation curve that's what the structure feels, right? So Probably deformation-based or performance-based analysis and design is probably the way of the future here. I don't disagree with you there. But when you say ultimate resistance, you made the statement that that end users look at the ultimate resistance, which is what people think the high strain dynamic test provides. I guess I would say the very well-known fact that high strain dynamic testing underestimates resistance when a pile is at refusal. I mean, by definition, it has to underestimate it because we're not mobilizing. So instead of saying, at least to me, when I hear the end user calls it the ultimate resistance, I think it's important to say that's the end user should recognize that's the mobilized resistance, which for a pile at refusal, by definition, is quite a bit less than the ultimate or nominal resistance. I think there's a difference there. And let's start there. Can we all agree that at refusal, high strain dynamic testing is an underestimate?
Yeah, but yes, but I think the same can be said for the static load test, where you see somebody has designed it on a piece of paper, say to a factor of safety of 2, and they load a foundation to 300 kips, and it's still on the elastic portion of the curve. Well, we know from that static load test, we have not reached the ultimate resistance either, because we have not mobilized the strength, we have not moved it enough. So I'm not sure that shortcoming of a pile refusal is a shortcoming of the dynamic test. It's just the fact that a static load test has that same issue of not moving the element enough to mobilize its full strength. And yeah, people have to present the result just as I would present that with a static load test case of we didn't reach geotechnical failure. We did a proof test essentially. There's more there. How much is there? You can draw hyperbolic curves, et cetera, try to figure that out. But yeah, I agree. It's not the ultimate resistance, but I don't know that that's a shortcoming of the dynamic testing. I think it's just a shortcoming of the driving system cannot move the pile, just like a hydraulic jack might not be able to do the same.
Fair enough.
Yeah. Wow, that was excellent. I keep swinging between the two of you because each one say a very good argument, convinced me completely, and then the other one counteract and it's like, yeah, that convinced me better. So it just keeps going back and forth. Lucky, you want to come back?
Yes, I've been here.
What do you think about this so far?
Well, I got to give it to both of them. When we started, I really loved how they both went back to the roots and started talking about how PDA, evolved. When did they start talking about PDA in the industry and everything else, and how they were introduced to PDA as well. And for a few minutes, I was a little, worried because they were very quiet and they were very, well behaving until Paul made a comment and, Greg, you could see his face, going red a little bit. Blood was boiling there a little bit. So that was really cool. Thanks for doing that, Paul. We knew you would do this. You definitely would not be disappointing to us. And at the same time, I think I really like how they both gave in the good and bad, examples of the projects, which definitely makes sense from the perspective of, as Greg said, his realm is testing, providing guidance and advocating for PDA. And Paul says like his realm is just reviewing. He never goes out to test and things like that. And, you could see both their perspectives back and forth. And, Paul said, as a client, you always look for a number out of the box, which is very true. It can be for this testing or it can be for anything else. Client just wants one simple answer, and that is something that would help them. So I really enjoy how they are bringing out good, bad, and ugly of PDA and also about themselves a little bit. Enjoying listening to that. So you can see from their conversation after the first round what we have a glimpse of in the other 2 rounds. And I'm looking forward to watching that. Good job, both of you.
Excellent.
Yeah.
So, all right. So I guess, are we ready for round 2? You guys feel relaxed already and go back?
What's
Excellent.
next? You're going to tell me Paul likes to use the EN formula to design piles, right?
Yeah, he's going back to that. There is nothing better than that, right? Excellent. So let's go to round two. And let me start with round two with something that Paul said. And this obviously goes for you, Greg, which Paul said the problem with PDA is start from the name itself, like the dynamic testing, right? Because, and I'll be very neutral here, but obviously when we were all in school, we learned, and especially if we spend a lot of time in the lab, we realized very quickly that soil reacts differently if it's a slow rate loading or if it's high rate, right? I mean, if like, I grew up in Colombia, and then obviously clay is everywhere in Bogota. So I spent a lot of time doing unconfined compressions of clay. And it's, I mean, obviously depending the rate that you fail the specimen, you're going to have a different resistance and the isotac behavior that we know apply to different materials. So do you have an answer to that accusation that he did that you never really have the chance to answer before?
Well, anybody who knows me, especially the contractors, if they'll call me with a question, I'll always answer it, it depends. And that's really the beauty about soil. When even somebody says, what's the strength of a soil? It depends. Are you pulling it? Are you pushing it? How long is it sitting there? Has it got some aging effects? It's just, clay is not a clay is not a clay. And, things change with time without us even monkeying around and sticking foundations into it. So even if a soil's been sitting there for millions of years, the instance we stick something in the ground, we've just changed that state of stress now, and its new state of stress is brand new compared to the millennia that it's been sitting there. But I think a lot of those issues are things that people have brought up since its infancy. I mean, the physics behind the dynamic testing is simple Newton force equals mass times acceleration, all these types of things that have been around for a long, long time. And it just took us, into the 1900s to get instrumentation that was able to measure something that, let's face it, is a pretty violent act to such a precise value to even attempt to make some of these measurements. So yeah, I think all of those issues that you're bringing up are true, and anybody who says the strength of a soil is a single number needs to check where they sent their college tuition, I think. But I think just history and the doubt and the suspicions or questions that should be asked, I think for the most part have been vetted, and it's still evolving and improving. And I think where, like I said, with open-ended pipes and some things like that, you got to be careful and say, this method it just might not give us the answer that we think we should be getting from the test. So yeah, I think the dynamic part of it is in the name. It's not a hidden fact, and the basics of the dynamic test is to separate out those dynamic effects from the static effects, or the total effects, I should say, and come up with that static resistance, which, in general, I think it does a good job at.
Yeah, so I think that's the point of contention. I think in some places, in some systems, it does do a fine job. There are other less well-known instances, geologies, where it doesn't do such a great job. And I guess the issue, even though all these issues have been brought up in the past, they're not well publicized. They're not broadcast. They're not published, and that's a shame in our industry. And I think it's to the point where we call these test piles. That's not. I don't know that that's a fair statement to tell an owner that we're giving them a test pile when there's so much uncertainty with respect to the dynamic shear strength, the cyclic loading effects, damping. Anytime we got to put something on semi-log paper or semi-log graph, we know we don't know it very well. So that's damping to a T. And so I think these limitations, which every test has limitations, everything we do has limitations. Those limitations need to be known. I think as an industry, we need to do a better job of educating the owners and the end users on what the limitations are. And I think if high strain dynamic testing has become a commodity where the only barrier to entry into the industry is to have the money to buy the equipment, I think sometimes we lose that appreciation for the limitations, and all we're looking to do is find the next high strain dynamic testing job.
All right, Greg, you have anything to add?
Well, I guess I will say this from my experience, that high strain dynamic testing, like any deep foundation endeavor, can be pretty humbling. I feel that, from my involvement in the testing, you go out on that site and you have a target on your back, especially if you're on, say, some design build contractor, and you told the contractor, drive it to this depth and thou shalt get this sort of resistance. And you get out there and you run the test and you don't get it. And they say, now what? Now what do we do? And when you realize the time and money that is now, that you're standing in between because you didn't get it right, it's very humbling. There's probably a lot of things that, let's go back to the shallow foundations. Not a lot of people are doing, low displacement tests on shallow foundations, and okay, maybe ignorance is bliss, or maybe we figure it's conservative enough, but to be out there and actually get that number, and hopefully it's very close to what you predicted, can be quite humbling at times. I mean, I'm a person too, that if I design something for a safety factor of 2 and we measure a 3, the contractor may say, great, let's move on. Let's go. This is what we're doing. I think, well, you're leaving a lot of money on the table, and, however much you could save in pile lengths, and thinking back about how much we argued about my geotechnical fee, it's a little disheartening, but yeah, it can be very humbling to say, here's a number that I'm measuring with this device. It's not the number I thought it was going to be. And as Paul's alluding to, it's not the number that it would be under a static load as well.
Yeah, no, I mean, it's interesting. It's interesting going into a little bit of what you mentioned before, Paul. Obviously, when we get into the PDA, there is things that are different than the rest of our geotech practice, right? I mean, and you kind of mentioned about damping, right? And quake, I guess. So let's talk about these variables for a second, because I don't think anyone that goes through a typical geotech program or something like that learn these variables, right? And then when we start learning the technology, we are referred to a table, right? And like, well, this is the table. Depending on the soil, you pick this, but at some point they look kind of like a black magic thing, right? It's something that is not a property of the soil that you learn fundamentally or anything like that. So I guess, Paul, if you want to go back to kind of that idea that you were elaborating before and
Sure.
criticize that if you want.
Well, I'll focus on quake. I mean, I think that's the biggest player. And before I get on my tirade here, I will acknowledge I'm a firm believer in GRL WEAP. I use the wave equation program all the time on a daily basis. I find it has great use for the things that we do in our practice. So I'm a big believer in WEAP, and I think it's an important tool in the toolbox.
Yes.
When we talk about quake, what are we talking about? Something I never learned in school, not even graduate school. So it's something I had to kind of learn on the fly. I think probably most people are in that same boat, unless they were focused on high strain dynamic testing as part of their research in graduate school or something. But so when we talk about quake, it's resistance divided by the stiffness of the soil or rock. And really the driver is the denominator there, the soil stiffness. So if we're driving a pile to hard rock, and the table that you alluded to, Sebastian, is use 0.04. Well, when our company, I hope our engineers are listening to this, when we do drivability, it's not just one run. We may run 50, computer time is cheap. We may run 50 simulations for one hammer and one pile by doing a sensitivity study of all the inputs. And what we almost always find is the biggest player is toe quake. If you get the toe quake wrong, resistances, driving stresses are vastly different than what are measured. And so by just picking a value out of the table and plugging it in and saying that's the value, I think it's very short-sighted. I think it's incumbent upon the engineer to do a sensitivity analysis and figure out what are the players, what parameters play the most role. And what we find is a lot of times, at least for piles on rock, the toe quake is giant, right? I mean, we'll either say we're going to overstress the pile, or we're going to show a resistance that's through the roof. But if that quake is wrong, things are quite a bit different in the field. So it is something you have to learn. I had to learn on the fly. And so maybe, Greg, I'll turn it over to you when you came out of school, were you a master of quake and all the other inputs that go into this.
He learned it in high school. So
Yeah. Well, I did learn Newton's laws in high school, but yeah, the quake part is a little bit different. And the term is it's more, yeah, the displacement, you have to move something to go sort of from the elastic to the plastic standpoint. So that's sort of that quake value is in inches or millimeters. And so, yeah, you can have these high quake soils where the pile will move a lot, but you won't get any permanent movement of the pile. It's rebounding a lot. So you can get a relatively high driving resistance that doesn't necessarily corroborate a high soil strength. But I think we're moving over into the wave equation and driving formula now versus maybe the dynamic testing. But the WEEP program is, I don't know what you can buy the thing for, $1,500 or something like that. But I was half joking before, but I still see people using the engineering news formula, which, I think was first proposed in 1880, around the same time the telephone was invented. And we can see what the telephone looks like nowadays compared to, but that formula still hasn't changed. And there's other driving formulas that are out there. I guess when the more variables you put in, the more correct you think you are. And now that you have to put it in a spreadsheet, it must be more better, because I need an Excel spreadsheet to do this now. But I guess I agree with Paul that, the wave equation analysis, at least it attempts to take into consideration a lot of these variables. I mean, you can do the math, I guess, but if you did the EN formula for a 100-foot pipe pile that's end bearing, or a 50-foot open-ended pipe pile that's skin friction, or a 20-foot concrete pile, if you use the same hammer, you run that calculation and you're going to get the exact same answer, which, my fifth grader could tell you that just doesn't make sense. So the tool is very powerful. But yeah, I think the way it should be used is, as Paul mentioned, to use it for sensitivity analyses. And hopefully you can get within the realm of, it could be this or it could be that. And is there a hammer that you can use maybe out there that will satisfy the conditions, whether it's a little bit to the left or a little bit to the right of what you have in your model. But I think what Paul's really getting at is, if you are trying to eliminate load testing and just use the wave equation, say, if you drive it to this blow count, this is your resistance, period.
Well, I guess maybe Sebastian, maybe the terminology in the question, correct me if I'm wrong, but when you asked about quake, in my mind, quake is an output of the dynamic testing, at least per that user's interpretation. It is a direct input into drivability analysis with WEEP. But really, I think maybe the right term that we should be talking about now, as it relates to high strain dynamic testing, is the set, right? Because it's the amount of set.
Right. Yeah, right.
It's the displacement, I'll say, at the toe, where did we displace the element, the foundation, enough to mobilize what we would call the nominal or ultimate resistance. At refusal, of course, the answer to that question is no. We don't. We can't. All we're measuring at refusal is the energy of the hammer. Maybe some other things with some fancy signal matching, if it's correct and the residual stress analysis is done properly. But I think what we should be talking about is set. A pile that's driven that has, in my mind, my experience, I feel like the high strain dynamic sweet spot is when we're in about that 7 to 10 blows an inch, maybe 7 to 9 blows an inch. I think that's where we can get realistic values out of our high strain dynamic testing as they relate to static estimates, where we have oversized hammers or big hammers, which are good for the contractor for production, where we're going in at 2, 3, 4 blows an inch. I don't believe that we're getting I don't believe that we can produce realistic estimates of static resistance because of the dynamic effects. I don't think we capture them very well. On the other side, if we're at refusal, we don't have enough set to mobilize the full base or toe resistance in my judgment. So I think that is a limitation of dynamic testing. I think it's a well-known limitation.
Greg, you have anything to add on that?
Yeah, I agree. I think there are some limitations with that. And I would still go back, I guess, if we're kind of batting around the gold standard of a static load test, that, too many times I see just a top-down static load test, say. No instrumentation to measure unit side shear, no telltales, no, you don't know if the bottom is moving or not. You know what the top is doing, but what the bottom is doing. So, you know, I know Paul keeps harping on the true answer is the static load test.
I notice.
Yeah, which I do appreciate the fact that if Paul's looking at the curves in their entirety from the 0, and even considering, you know, residual stresses and things like that, and that's the response of a pile or a foundation under a load. I think that's the biggest thing is the performance, and whether the toe is mobilizing it or not. Let's face it, the load is at the top of the element, the shears, the moments, other things as well. And we're trying to get an idea of, are we meeting some sort of deflection criteria under a certain load that we are going to use going forward. So I think there's just that shortcoming that could be said for, you know, static or dynamic test.
I guess I tend to disagree on that, Greg. I mean, at the static test, assuming we have an adequate reaction system set up, you know, maybe we're limited by the jack, but we can just push harder. On a dynamic test, we're limited by the hammer. And it make me, you know, I don't think any of us would see the economy in mobilizing a larger hammer, larger leads, larger crane, just to hit a pile harder so that we can try and mobilize more toe resistance. It just doesn't seem that practical to me.
Well, I think mobilizing a bigger hammer is probably cheaper than getting a bigger reaction system out there.
Not if the bigger reaction system were already built and installed, right? I mean, we wouldn't install a second reaction frame. We just size the first one to have enough.
That's the key.
Sure.
I think too many times the expense of a static load test is put forth, and like I said, for a couple pennies on the dollar to put some more instrumentation and make sure that you're hopefully running it to geotechnical failure, or if you're not because you're on rock or something, then most of the codes are saying it's a function of your material strength, right? Your maximum load can only be a percentage of your steel strength.
Yeah, like the 90%.
Which I guess that's something that we've run across both with, say, driving formula or wave equation. I don't want to hijack this, but I think some of the codes will apply different resistance factors or safety factors to your method of testing, right? Usually the static load test being the quote unquote gold standard. You have the best number, the lowest safety factor, highest resistance value, right? From that standpoint. The dynamic testing might be next, and then the driving formula or wave equation, and then maybe the driving formula next. And it's quite interesting that if you look at some of the codes, I don't have a calculator to do the math and all this here, and I don't think anybody really cares to go through it, but
I do have my calculator if you need it. always calculator on my hand.
Yeah, okay. If the code may allow that you can design, you can put a maximum load on a pile that's, say, 50% of the yield strength of the steel, right? So say at HP 12 by 53, that's 25 KSF times, what is it, 15.5 square inches, right? So maybe I forget, maybe it's like 300 kips or something like that.
387 and a half, Greg.
Yeah.
Yes.
But then if you use, say, a wave equation, your resistance factor is usually somewhere on the order of, say, maybe 0.4 or something like that. So the ultimate resistance then that you have to drive the pile to is actually a higher stress, just by dumb math, than the strength of the steel itself, if that makes sense. So sometimes you're doing the dynamic test just to use a different resistance factor, not because you're trying to mobilize and show that the pile the soil can hold more load. You're just trying to reduce your ultimate resistance target value to something that's less than the yield strength of the steel. I don't know if that makes sense without writing it down, but it's it's a thing. Sometimes we do PDA, not to necessarily confirm the resistance per se, but just that the resistance target has to be lower so that when you drive the pile, you're not overstressing it.
I think that's the case of the tail wagging the dog.
Yeah, I mean, if you have 20, I know, Paul, you're a big drilled shaft guy, and I forget who said it, but I remember one time listening to a presentation. It was about load testing and how much load testing, the cost up front looks like a large value, but in the end can be pennies on the dollar and save you a lot of money. But with drilled shafts, you're cutting out 10,000 psi rock to drop in 4,000 psi concrete. So yeah, sometimes things don't quite add up.
We're going there, right? We're going to that. Yeah, Paul.
This was interesting.
Yes.
Was really interesting.
It is.
Because I was happy when they started with point of contention a little bit, and then I could see how they agree and disagree on certain things, which actually makes a lot of sense. Makes a lot of sense from how Paul is looking at and Greg is looking at, and I think it's a good point that Paul made with respect to software systems, right? Different softwares and how much understanding can we have, and how the understanding changes over a period of time. Us being in the industry and us being publicizing what we can do, what we can't do. So that was really good point from Paul. And I think he also did say about not well publicized, right? I think as you remember, the first series was of the podcast was Interview with the Survivor. The reason why we did that was people don't like to talk about failures, exactly like what we are talking about, like what went wrong. We never want to talk about, right? We always want to talk about everything that went well. So I think it was good that those points were brought out. And at the same time, I see a lot of initiatives coming out of this conversation. I think everyone who are very close to PDA testing and also drill shaft and the foundations that we talk about, I think there will be a few good initiatives that will come out. And who knows, maybe for the next year's project fund, Paul will be applying for one and Greg will be applying for one, or they both will be working together.
Yeah, I don't know what Paul's doing this weekend, but he needs to start writing this paper on these contradictory results I keep hearing so much about. I'm very interested in that.
I know.
And Lucky, yeah. I would argue somewhat. I always think when I go to the conferences, I said, boy, if my wife were here listening to this, she'd think everything is falling down because it's like the news. It's another great project. Nobody wants to hear about that. They want to hear about these things that kind of go wrong. So maybe Paul will be able to enlighten us with some great case history showing the dynamic test is failing.
Yeah, Sebastian, Paul, I think I have an idea for one of the conferences in the future. Maybe we should have a session which is only about failures. No talking about. I don't know how much people would want to share.
Yeah, the liability thing and the image.
But think about it, Sebastian. The Interview with the Survivor, we had the same issue right before starting the series. But there were people who came out and said what they had to say about the projects, and we learned a lot from it. So I see this going very well. After everyone listening to this, when it comes out, and I'm looking forward to seeing what is the conclusion of these two and where we will stand with respect to Paul and Greg. And I'm hoping to have the famous Paul's laugh before we end. Let's see. So good luck. Don't disappoint me.
They will not.
Well, I think we have to be careful about I'm not, the projects that I'm referring to where the high strain dynamic testing underestimated the static resistance. The projects, there were no failures. It was the only failure was if we would have relied solely on high strain dynamic testing, we would have put an unnecessarily amount more of steel into the ground. That's not a failure. The projects would not fail. It would be an economical question for sure, but things aren't falling down because of this. We're not as optimal as we could be in some cases.
That's a great point, Paul, because I think, I mean, of course, Greg was saying it as a joke, right? And when say like, show me the cases where things are failing, because yeah, I mean, I think we recognize that, we treat this with a lot of respect. Obviously, we all admire, and deeply respect what GRL has done on PDI. I mean, it has absolutely revolutionized our industry. We're having these discussions for fun, right? And I mean, obviously we're super nerds, and it's nice to find other people that are equally nerd that want to have this. I don't know, man. I don't think this conversation is easy to have with many group of friends.
No.
I mean, it's very centered. So it's awesome to have like, two reference in the industry like you guys going in this detail. But yeah, we all respect and recognize the amazing job GRL and PDI have done. And we are just discussing this for fun because there are things that we see, but it's extremely important for anyone listening to understand that, yes, as you pointed out, Paul, this is not failures, right? I mean, we're not talking failures. We're just talking discrepancies that are still covered under the design, and they are still covered by the factors of safety and things that we use. So even though it not be an exact match, it's far from really being a risk, or compromising the safety of the structures that we construct these days, correct?
Yeah. And I think, Sebastian, Paul just hit the nail on the head. Like, I know, of course, this is not going to fail the structure for any reason, but I think at the same time, all the examples they were talking about, Paul and Greg both, I think it would be nice to come out and talk about these examples where things did not go as they expected and how that was rectified. What are the things to watch out for on projects? And as Paul was saying, everything boils down to money, right, Greg? Everything boils down to money, to the person we are working for. And if we can show that, what makes the small tweaks that we have to do in small understandings, and of course, there is a lot of research that is left on the road, right, that we have to get to. From 1900, as you said, Greg, we have come a long way, and there is a long way to go too. So technology is changing, technology is growing. And so I see a lot coming out of this conversation. Thank you to both of you.
Yeah, I think the dynamic testing is hopefully showing an economic advantage, but not having a detrimental effect on performance, obviously. So I would tend to agree that if most of the time the dynamic test is more conservative maybe than what the static load test might show, hopefully it's rarely the other way around. But if it is, then with the safety factors and resistance factors, we should still not have a performance issue.
All right, I think we're ready for round 3, correct?
Yes, we're ready for round 3.
Excellent. All right, so we're entering now the conclusion, and we're moving into, I guess, let's try to find a realistic consensus. As I said at the, I guess at the intermission, there is nothing but respect, absolute admiration, absolute respect to GRL and PDI. They have revolutionized the industry. They have introduced a tool that have changed significantly the way that we do things, and it's absolutely safe. And we're just talking about these discrepancies. But yeah, I mean, just to put it out there that we have complete respect to what they do, and we have complete admiration and support. And this is not intended to be disrespectful to anything. And we're just exploring very nerdy conversations among experts just to discuss this because it's fun. That's the only reason we're doing it. So moving into the consensus part, I guess, well, let's start talking about those cases that we said it worked well, but it may not work well. And let's just try to start putting. So I guess, Paul, if you want to start, talking about in your experience, let's say, are meaningful results on, and you kind of touch a little bit, but let's just do it kind of as a group. As these meaningful results of PDA on hard rock, what about also hard clay, glacial tilts, very dense sand? I mean, what are the problematic situations that you think this will be a disaster, and what are the situations that you think it could be something good?
Okay, so I mean, I think anytime a pile is at refusal, we are going to underestimate the nominal resistance with high strain dynamic testing by definition, a well-known limitation. I think conditions that aren't very favorable for dynamic testing, or for getting a reasonable static resistance out of dynamic testing, are soils that are highly sensitive, saturated soils that are of young geologic age. I've seen issues with those. Silts are always a problem, in my judgment. Like Greg said at the very beginning, a clay is not a clay is not a clay. There are some clays that don't behave well under dynamic loading. Cyclic loading, a whole nother issue. And so I think for high strain dynamic testing to be a reasonable estimate of static resistance, it has to be calibrated locally to static load tests. And I think Greg operates mostly in regions where that has been done. And I think he's probably developed in his practice a great reliability for what he gets out of his measurement. And he probably some time ago related that to static load test results, I imagine. When those conditions exist, it can be a very useful tool. It is a useful tool. But there are situations that need to be brought forth in the industry where it does not provide the most reasonable estimate of static resistance. I think concrete piles, stiff piles and sand, displacement piles like concrete piles in a sand or even a unsaturated soil, I believe if you're in the sweet spot with the driving system, high strain dynamic testing can provide a very reasonable estimate. But there are lots of other locations where that's not the case. So Greg, I'll let you shoot at me.
Yeah, I agree. I agree that the displacement during the test is a big part of the dynamic test method. There's no getting around that. That test is run as you're impacting a pile, dropping a weight on, a cast in place pile, whatever it is, but you have to move the pile a reasonable amount to stretch the soil, strain the soil to hopefully measure its maximum strength. As you know, Paul, with the drilled shafts too, we get into these, situations and maybe you have to move the side a tenth of an inch, a quarter inch max to mobilize the maximum skin friction, but you have to move the toe, a lot more to get the ultimate resistance at the bottom. And you may never get the ultimate resistance in a sand. You just keep pushing it, and your resistance just keeps getting larger and larger and larger. But at some point, the top of the element exceeds some reasonable displacement. I guess with respect to, driving piles to refusal on rock and things like that, again, I feel like a lot of times the codes and what the engineers are doing is just saying the load on the pile is, 25% of the yield strength of the steel, 30%, 50%, whatever it is. So whether you're mobilizing the end bearing strength of the soil or rock, in some ways it's irrelevant because you're still limited to what the steel stress is allowed. So in some cases you're mainly doing a proof test to say, yeah, it'll support that, but if there's more there, we can't take advantage of that anyway.
But what about, Greg, what about for a pile driven to refusal in say highly glaciated, heavily over consolidated clay? If you've got a pile, say a 16-inch closed in a pipe pile driven with a D30, and you tip it, you're at refusal in a clay, a really stiff clay. Do the rules for rock still apply? I don't think they do.
Right. Yeah, and again, that's it. People, I feel, do take pot shots at dynamic testing of it's not mobilizing the ultimate resistance. But as I said before, I feel that same exact argument can be made with a static load test. You still have to move it enough to mobilize its ultimate strength. And then the bigger point is when you do that, what's the top of the pile doing? And is that meeting your performance requirements?
Yeah, I agree with that. But something I'm still hung up a little bit on. The illustration you made about a drilled shaft in sand, it just keeps mobilizing. It develops more unit base resistance as the deformation keeps increasing. So you keep pushing and it keeps giving you more resistance, but there's some practical limit. Is there a practical limit at the strength limit state? So in my mind, the serviceability, that's where it comes, the performance, the load settlement performance is governs, but at the strength limit state, and I don't think geotechnical engineers are very good at this, at the strength limit state, shouldn't we be designing for a state of plunging failure?
Yeah, I mean, ideally, with the dynamic test or the static load test, you'll see that in your result, that clearly you can throw whatever person's last name you'd like to and call what the ultimate resistance is, but it sure would be nice to see that at some point, as you add load, you can't add any more load. It's just displacing without any additional load, a plunging failure. And then we kind of know what that edge is of the cliff, I guess.
All right. All right. I guess moving on into something that you guys also mentioned. Okay, so we talk about the soils and what could be different, but what about the piles? I mean, are we abusing the method for different piles that should not be used for this? I mean, let's start with typical steel H piles, then pipe piles, and then we start kind of expanding, right, into, is this proper to an overcast pile? Is this, can we say that this is perfectly usable for concrete piles for everything? So I guess, Greg, let's go first with you. You think it's a technology that we should apply? I mean, it's as you say, it is science, it's principles, it's mechanics, right? It shouldn't really matter what pile are you doing. You think that's true, or you think that there are certain piles that you absolutely need to avoid?
Well, I mean, I would say that, with the cast in place elements, especially those where the geometry is a little bit more unknown, that leads to one more uncertainty. If you're already concerned about the toe quakes and some of the variables, say in the signal matching, the geometry is then now also in question. So, a lot of the high strain dynamic testing assumes uniformity. We sometimes have composite piles, we call them, with a concrete top for scour, corrosion resistance, lateral stability, and then maybe an H pile sticking off the bottom could be longer than the top concrete. And even though that's non-uniform in the signal matching program, we can still, we know what that geometry is and can model it. But yeah, an uncased drilled shaft or a CFA pile, you don't know with certainty what those values are. Of course, with static load testing and putting strain gauges and trying to get unit side shears and things, you're also making some assumptions about maybe the areas and some of those. But yeah, I'm not as comfortable using that method with a cast in place pile or one of unknown geometry.
Well, I'll just jump in and say, I mean, the high strain dynamic testing is being applied to every deep foundation element we could think of. I mean, my friend Brandon at GRL in Houston, I mean, he and some of his colleagues are applying it to helical piles, which I think's, it's very interesting. I can imagine how complicated that must be. I think there's still a bit of arm waving with respect to interpretation of high strain dynamic tests under the best circumstances. And I mean, I can only imagine how difficult it would be to interpret it for a helical pile. I've seen with steel piles, and of course, this test method is done on steel piles all the time. But steel's relatively flexible, and if you have sensitive soils that are prone to dynamic effects, we can see. I mean, we've seen what we term unzipping, is that as the pile, as a wave propagates down the pile, and it's flexible, and it sort of like an accordion. And the resistance along the pile that's offered by the soil is not uniform, and it unzips with time. And so even though the measurement itself's been done on these types of piles for, 50 years now, it's still a phenomena that happens. It's not well understood, not well publicized. And so I think that's a drawback to the method itself, or maybe our understanding of the method. The perfect pile type, like I said, I think are displacement piles that are really stiff. That's my experience. For cast in place piles, I've yet to see one where we actually moved it had enough set to mobilize a reasonable guess at the base resistance. I think that's usually the drawback. And to bring out a weight or a hammer that's big enough to do it, then we kind of get the other problem. Now we're overstressing the element, and nobody wants to break it. If things start cracking, the interpretation of strains and wave propagation, they get pretty hairy pretty quick.
Well, I guess, yeah, I hear what you're saying, Paul. My experience is, I would say in general, the dynamic testing provides a more conservative result if it's not close to the static result. Using driving formulas in the past, I mean, supposedly the EN formula is, based on a safety factor of 6. I think, one of the big things with the dynamic testing is we're not pushing things to an unsafe level. I think we're just, we're trying to get away from safety factors of 6 and get closer to things like 2, 2.5, where there's an economic savings without being so conservative. And I think when I led off this debate, this rumble, again, getting a consolidated undrained shear strength test, people think that's the strength of the soil, and especially in some softer materials, and trying to sample it and get it back to the lab and extrude it. And so that answer, that's quote unquote the gold standard, has some issues with it as well. And some other in situ tests, DMT or CPT with correlations and to see trends, I think is pretty valuable, especially as a geotechnical engineer, when we know things are not exactly the same from here to 20 feet away to 30 feet away. That is it more valuable to have 1,000 data points that may be 90% of the resistance versus one value that is supposedly the right one at one tip elevation. I just think the amount of information that you get, and if anything, maybe you're a little conservative on those capacity values, and the price and economy. There's just a lot of great information that you can get that I don't think you're necessarily being unsafe about it, but we're trying to make things more economical. So I'm a proponent from that standpoint of, I get a lot more data, and if it's not 100% correct and it's off by a little bit, I sometimes would take that over just the one point that may be quote unquote perfect, which again, we can debate whether that's the actual number or not.
Yeah, I think where you're going, Greg, is perfection is the worst enemy of very good, right? And we shouldn't. But interesting. I don't know, Paul, you have anything to add? You're good with that?
No, I mean, I certainly understand and appreciate that perspective. I can't disagree with it, but I would say, that when he made the point of, we're trying to get to a factor safety of 2 or 2.5, I guess I would say in reality, that's more like a factor safety of 3, 3.5, because of what I think are the lower bound estimates that are being generated. And so, in the idea of being sustainable and economical and whatnot, I think we can do better. I think we should do better.
What about the history on this factor of safety too? Because I sometimes feel that we were sold this promise, especially when we go to LRFD, that it was going to be a lot of calibrations, and this resistant factor, with PDA was going to change and it's going to come closer to 1.0. I'm like getting closer and closer. I guess starting with you, Paul, you think in the industry we really have advanced in the last 20 years to get this closer, or you think that it was a promise that, I don't know, it just stay there and we keep doing PDAs, we keep doing static load tests, but we don't really try to close that gap? It's kind of going into what you were saying on the factor of safety.
I think you hit the nail on the head. So when I first started my career, for the first, 8 or 10 years, we were still using ASD design, where the factor of safety basically included all the unknown, and where the geotechnical engineers made their mistakes, at least in my mind, the geotechnical engineer did not own that entire factor of safety. All of the unknown and uncertainty from the loads and from the structural side and construction side were also dumped into that factor of safety. And so we sort of had these blinders on that said, okay, well, I got a factor of safety of 3. Well, not really. You may only own half of that factor of safety. Mm-hmm. So from that perspective, I think the switch to LRFD, it's a much more logical design framework in my mind. I'm a big proponent of the LRFD design approach. Have we closed the gap and are we getting better? I think it's just the same, to be honest with you. I don't know that we've really furthered our understanding of foundation performance and included or are taking advantage of those performance-based specs. Most the AASHTO code isn't performance-based really. It's a capacity-based approach, and so I think there's still some low-hanging fruit that we could grab, and I truly believe that we are starting to head this way with some of the research that FHWA is funding, where we might be rethinking limit states. I think we're going the right direction, but I don't think the needle's moved very far so far, Sebastian.
All right, Greg, you want to answer that?
Yeah, I don't understand all the statistics part, and I know Paul, your colleague there, Eric, has done a bunch with some of this resistance factors and things like that. But yeah, we've just kind of taken the inverse of the safety factor, so to speak, at this point. I guess for me, a little bit of the hard thing is, if you have 50 KSI steel that comes out of the mill, there's statistics about, how close to 50 is that every time, and it's a man-made manufactured material, and it's pretty darn close to 50 every single time. With soil, like I said, what's the right answer? It depends on the time. Even when we're doing these tests at a week, 2 weeks after, the building might not be loading these foundations for months to months. So are you getting additional resistance in the system over time? With pile caps and groups, are you densifying soils and actually making the resistance higher than just the test pile sitting alone out in the field? The group effects that, with overlapping and sharing. So a lot of the focus is on a single element, which we all know, that's not necessarily the norm, especially on buildings where you have caps contacting the ground, et cetera, et cetera. So our focus is purely on this test at this time, at this tip elevation. But as Paul alludes to, the static load deflection curve, that's how the pile is going to behave. And I get that, but that's not necessarily how it's going to behave in the end product with the rest of the structural system around it either. So we may sharpen the pencil and get closer and closer and closer, but are we really going to get to the in situ performance of the element once we're all done? I'm not sure.
Paul, anything to add? You're satisfied with that answer?
Yeah, I mean, I come from the bridge world where we have to design for scour, and so a lot of the time, a lot of things Greg's talking about, the mat or the cap in contact with the soil, that's not included in the design because it's wished away due to a lot of things that are different than the building world. So I have no heartburn with what Greg said. I mean, I agree. We're making a measurement at a certain time, and it's not the final configuration, but it's the best we can do for now.
No, yeah, I agree. I mean, I think this round is to get the consensus that we're really getting to that point, right? Realizing limitations and things like that. But I guess one aspect that we didn't really touch that much, or I think we mentioned a little bit, but not really explored it, is the user dependent, right? I mean, it's obviously we know that it depends a lot on who's doing the test, what are they using, what is specific data point, what is specific, So, I mean, do you think that, what is the average experience that we need really in practice for someone to do this? I mean, do you think it's a dangerous thing that is like that? Obviously, GRL and PDI and all that, they have certifications that people can take, and obviously you should have one of those certifications to really professionally do one of these tests, right? But do you think it's enough, or you think that a technology that is that dependent on that should really progress into another direction? Like, let me just explain it a different way. Anyone can read a dial gauge doing a static load test, right? And I mean, if it's a calibrated gauge and all that, there is little mistake or potential for mistake on somebody making a reading. But when we go to PDA, it's a whole different world, right? It depends in so many variables. So what's your opinion on that, Greg? I mean, do you think that in reality is not a problem, and the industry has a very good standard to making sure that every operator that is doing that is doing a good job? Or you think that it's something that could be done better?
Yeah, I think as engineers, there's a responsibility for, it's like with finite elements and things like that. I mean, garbage in, garbage out, right? And so I think the key is recognizing when you have garbage going in and don't report results and things like that. So yeah, there has to be some level of comfort that I know good data and I know bad data. And if it's good data, and again, cap WAP signal matching aside, some case method just based on the raw data can get you, at least, is it 300 kips, is it 700 kips type thing? And the variables you put in, are known with some certainty. But yeah, I think, and I hate to say it, but I've seen some data, I peer reviewed it, and I'm shocked at some of the dynamic testing 101 rules seem to be broken by people that I think have been doing the testing for quite some time. So yeah, I think the quote unquote certification process is a good thing. If you sit through the class and are a good test taker, could get a good grade. And if you've been doing the testing for 25 years and maybe aren't a great test taker, maybe you don't get quite as good a grade. So there's, just because you have a certification or a certain level, I'm not sure that it's always 100%, but at least it shows you sat through a class and have gone through and know what data is supposed to look like, and sort of the basics of use two strain gauges and things like that. And to know when the data I collected is just not, it's not valuable. Sometimes I see, you can't unsee things. I used to tell my kids when they get on the internet, if you see something, you can't unsee it. And there's engineers that, with CSL or PDA, they see the data and I look at it and say, oh, that result is just, it's not right because the data collection is poor. And then they always want me to justify, well, it said it was X. Now you're telling me that's not right. And it's almost like no data is better than that incorrect data, that you can't unsee that. And some people just can't get it out of their mind. So yeah, I think in some ways we do need to police it and make sure that there is the operators and the person doing the analysis and writing the report has some understanding of the method. I think a bigger picture is, as Paul maybe is alluding to, that if we're just testers versus engineers doing a test as well, just reporting the data and not saying in a footnote maybe somewhere that at this relatively high blow count, the number we're presenting in this report is not the ultimate. You have to understand that. And I think some testers may do a disservice that number in the table that's showing up, I'm telling you, is a conservative number. It's not gospel.
Excellent, Paul.
Sure. I mean, the certification, certainly it's a step in the right direction. I can appreciate the intent of raising the bar. And I truly believe that is the intent. Whether the bar has been raised, I'm not so sure. And I won't just say that to certification. I mean, a lot of people have a professional engineering license. What does it take to get that? A little bit of experience and passing a test. It really doesn't have anything to do with your ethics or your integrity, or beyond the test, your ability to do engineering. I think the certification could be seen in the same light. And as long as we're in a low bid world, as long as we operate in a low bid world, it's going to be a race to the bottom. And any commodity, which testing could become, will be pushing the boundaries of ethical or a person of integrity, who knows, like Greg said, when he sees garbage in and garbage out. In a low bid environment, that's a race to the bottom. It doesn't. Some of those people may not care that it's garbage in, garbage out. They're the low bid offer, and they got the work because they're cheap. I don't know how that could change with certification.
All right. Well, this absolutely was a fascinating discussion, right? I just have to say thank you to both of you for joining us today. As I said, it's an extremely nerdy conversation, and I don't know that many people that will be willing to go to this extent, especially on a Friday afternoon. So that is highly appreciated. And I think we said a lot of things that are good. I mean, we did not intend any disrespect to the method, to the technology, to the industry. We just question things that I think every engineer that has been working with these tools will have in their mind, and it's nice to have an open discussion about them. Correct?
Yeah. I think that they did very well, Sebastian. No blood spilled, just a few scratches, I would say.
Difference in opinion, I would say.
Difference in opinion, yeah. But, I think I really like how the conclusion, round 3, came all together at both of them alluding at the same factors and parameters that we have to really, really look into. For a successful design, and also, helping the client build the right thing. And, Paul and Greg actually talked about what is important to learn with the experience and using the technology and using, how to read the results that we get out of the PDA and other testing devices that we have. I really like. And Paul also gave a very good ending to certification, how important it is. It doesn't mean that if you have PE, that is the end of it and everything you say is we have to take it. That's really good. And we have had these conversations in many of the other episodes as well. And I really have to say, valuable conclusions from both of you. Thank you, Paul, and thank you, Greg. And, this has been fascinating. As Sebastian said, there will be a lot of people who will be coming up to you and engaging you, shaking your hand and engaging you in more discussions of what we just spoke about the next time they see you. So this concludes the episode of DFI Rumble. So we have to ask our listeners, don't forget to comment who won in this area. Was it Paul Axtell, who is a reviewer, or Greg Canivan, who actually does the PDA testing, knows a lot more about how the testing is done, or the industry? Let us know what you think. Thank you so much to all of you.
All right, thank you.
On behalf of DFI, we hope you enjoyed this episode. The views, information, and opinions expressed during Deep Foundation Institute's podcasts are solely those of the individuals involved and do not necessarily represent those of DFI. DFI does not verify or take responsibility for the accuracy of the information contained, nor does it warrant that the information contained herein is suitable for any general or specific use. The podcast is available for private, non-commercial use only. Editing, modification, or redistribution of this podcast is prohibited. Sponsored by ECA. Thanks for your time. Keep on surviving.